Okay, so we can start. And as promised, I would like to talk about a new chapter today, which is about the so-called indirect approach for optimal control, which we will derive using the Hamilton-Jacobi-Bellman equation. And I would like to give you some intuition of where it comes from. And then we really want to go through some examples to see how it can be used for computations. It's also the subject of the current exercise sheet, the one that you can do this week, but I think next week when Andrea is back, you can really actually do it. Okay, so it's chapter 12, and it's about the indirect approach. And it's also associated to a name of a famous Russian control scientist or optimal control scientist who was called Pontryagin, and who basically made this approach popular and invented part of it. And this is, maybe I should say, it all comes, it started with Euler and Lagrange many years ago, but Pontryagin really made it applicable for optimal control problems, in particular with inequality constraints. And a bit similar like the KKT conditions, nowadays everything that is, so to say, necessary optimality conditions, we call KKT conditions. Similar to this, everything that's related to the indirect approach we call now, so to say, following Pontryagins minimum principle. And maybe I should also say that in his original paper it was called the maximum principle, Pontryagins maximum principle. In our lecture we always minimize, so we will call it the minimum principle, okay? Maybe I should give this name already here, Pontryagins. Okay. And here you could either have maximum or minimum principle. And what we will present in many papers will be abbreviated to the PMP approach, the Pontryagin maximum principle approach. So when you see PMP, then it's related to what we do today. So let me start by deriving it, and as I promised already, I want to do it using the Hamilton-Jacobi-Bellman equation, and I want to look at it at EV at optimal solutions. So let me recall a few things that we know from the Hamilton-Jacobi-Bellman equation. You remember maybe that we derived this equation that says minus dj by dt is equal to the minimum over all u of a function that we call the Hamiltonian function that is evaluated at x and u, minimized over u, and then there was this crucial ingredient, namely the gradient of j with respect to x. So this was an evolution equation for the Hamilton-Jacobi for the value function, and it had a terminal condition, namely that x at the last time of our horizon would be equal to the terminal cost. Yeah? So maybe I should recall, because otherwise you don't have the data, right? Let me just recall the optimization problem that we look at all the time. It's the integral Lx u dt, 0 to big T plus e of x of big T, so the terminal cost, and then subject to x0 minus x0 being 0, and then x dot minus f of x and u also being 0 for t on the time horizon. So that's the optimization problem we will look at. Not changed, same as we did before, but just to get all the data on board. And you remember that this Hamiltonian function was something that we would define more generally. Not, I mean, for any lambda has the same dimension as the state, but it's actually related to the gradient of the cost to go function. And this function, the Hamiltonian function, was defined to be the running cost. The cost under the integral, or the Lagrange term of the cost, as it's sometimes called, plus lambda transpose times f of x and u. So you see this is a function of lambda, x and u. And so that's why it's called like this. And when we plug for the lambda the gradient of the value function, then we get this expression. And if we minimize it over u, we get the time derivative of the same function with respect to time. So that was what we have derived last time already. And what I want to do now is I want to look at the evolution of J along an optimal solution, and we will see that this gives us some conditions that are easier and that avoid solving in PDE. Maybe I should also recall one other thing, namely that the U, the optimal feedback control, which you could say, I mean, at the optimal solution, right, could be given by the argument that minimizes actually the Hamiltonian if you would know the optimal solution in X, then you could actually say, okay, then it must satisfy this equation at the X star of T, comma U. So you could actually plug this whole expression into, if you would know the optimal state trajectory, then you know it should satisfy this relation also to give you the optimal U. So that is nothing else than basically what we had above, but now looking for what is the optimizer. And what you observe is that because of the fact that here is only the gradient of the cost to go function, it would be enough. We don't need to know the J. We just need to know the gradient of the cost to go function at the optimal solution. And that's why we like to focus on it. Yeah? So the main observation here is U star of T only depends on which does it depend? On X star of T. Yeah? And the gradient in X direction of the cost at the optimal solution. And of course, but not on J. That's only the gradient of J. So we don't really care about the value of J, we only care about the gradient of J, and we only care about the gradient of J on the optimal solution. So it would be really useful if we would somehow get another set of equations that gives us this gradient, so to say, in a cheaper form than solving the Hamilton-Jacobi-Bellman equation. And that's what we want to do. And so let me just give you this one picture. Here's big T, here's 0, here's the state dimension, x. And if you think of the Hamilton-Jacobi-Bellman equation, it's basically describing a function J that lives in this space. And maybe let's make it, maybe it's not exactly the true picture because x might not be bounded, but basically on this domain we need to know the function J as in the third dimension. And at the very end we will have an initial value, for example this one. There will be an optimal solution somewhere in this whole thing. And along this optimal solution you could actually think of having, I mean here's some, if this is a value t, then the value here is x star of t, right? And at this value you will also have a gradient of the cost to go. That's basically, I mean, cost to go is too difficult to plot now into this whole landscape, or I didn't want to do it because I cannot do three-dimensional graphs so easily. I tried it at some points, you remember, then I did these pictures where I added such things, right? But I don't do it now. But the main point is, if you would know the gradient in this direction, basically the slope of that function J, at this point you would actually be able to compute the optimal control at that point using local minimization only. So the idea is generate only nabla xj of x star of t and t. And these things we will call lambda star of t. So these would be the optimal lambdas. And they will be related, of course, to Lagrange multipliers and so on. And we call these things the adjoint states. Or sometimes they are also called co-states, depends on, I don't know on what it depends, but people call it sometimes this, sometimes that. Okay? So we would really be interested in knowing the lambdas and the x's along the optimal trajectory, and if we would know them, then we could compute from them the controls. And so now let's just look at if we can derive an equation that the lambdas and the x's need to satisfy, which is based on the Hamilton-Jacobi-Bellman equation. So I would like to first do one little exercise in calculus, which is the following. So if you look at how does lambda star of t depend on t at the total time derivative. Yeah? So if you really think along the optimal trajectory, yeah? So you move here in this direction along the optimal trajectory, how does the lambda change if it has this meaning? Yeah? So it will be, of course, this whole thing depends on x star, on t and t itself. So if you differentiate it, you will have to differentiate first with respect to x and then with respect to t. So the differentiation with respect to x gives you actually a second derivative of this j at x star t comma t times the time derivative of x dot star of t. Yeah, so that's the first derivative, and the second part is now dj by dt at x star of t comma t. So this is what this how the lambda star would depend on. Oh, sorry. Here I forgot one thing. So this is wrong. This is because this is already the first derivative. So let me just keep it back. I could write it like this: x, and then here I have t by dt. That would be j. So I have another x and a d by dt. But now this is a partial derivative that only differentiates on that side. So we see that this is actually a bit related to what we see there on the Hamilton-Jacobi-Bellman equation. And let me just try to take this equation, this one, and differentiate partially with respect to x. So I will do a partial derivative of this x. And what I will get then is actually a minus d by dt of the gradient of x. I will omit the argument again, but it will always be x star and t, right? And then on the other side, I will differentiate it also with respect to with respect, to now partially differentiating this whole thing with respect to x. The first thing is I have here, maybe I write it first. So here what I will have is d by dx of the Hamilton-Jacobi-Bellman or this Hamilton function evaluated at x star of t, comma, gradient of x of j of x star of t, comma t, comma u star. And this u star, I will, it's actually this thing that I wrote down here. So it's the optimal u. And that implicitly depends, of course, also on x, because this, if you look at that, it's a function of x. But fortunately, because it's minimizing this whole function with respect to u, the partial derivative of this whole function with respect to that argument will be vanishing, so it's 0. So I can actually just regard the partial derivative with respect to the first and the second. Maybe I should call it a total derivative. It's because it's inside here, right? So, and what I will do now, I will put it. Let me just do it. So I will get the first argument here, and that will be dh by dx. And because I have a gradient here, I think I need to transpose that whole thing. Yeah, because a gradient is a transpose of this partial differentiation. And what I get here is now this thing. I omit the argument as a transpose. Then here I have the outer derivative and then the inner derivative, and then I transpose it. So what I get here is dh by d lambda. I call this already the lambda argument because in my definition I had the lambda there at this place. And then times d. Yeah, so now I have this. Now I directly get it. So that's the derivative of that whole thing with respect to x. So I get here the second derivative of that entry, and then the whole thing transposed, right? So that's this derivative, and that one will vanish. So I don't care how this depends on x because it will actually be vanishing. Okay. So now I have something that I can make use of, and we just move the blackboard up. So beautifully, I have this term here and this term, so I can see this and here, right? I need to just see what this means. So what is dH by d lambda? Yes?
Just a question.
Yes.
In the last line,
yes.
You wrote
This one.
the entire second term transposed?
Yes.
Because there is already a gradient in there, it's gradient squared.
Yeah, that's a symmetric metric, so that doesn't matter. So it's just a second derivative Hessian matrix. But basically, it would be nicer, or not nicer, it would be clumsy to write it all with indices, but then it's easier to be correct. But basically, if I write nabla x, I mean the transpose of the Jacobian. If I have already a column vector like this, and I differentiate it with respect to x again, then I get actually this expression, right? But that is then the true Jacobian of that, by the way. So that's why, yeah, because this is already transposed. Just notation. I mean, the second is, so to say, a new symbol. The first one I just identify with a transposed Jacobian. Maybe I write it down for safety. So if I have some function f from Rn to Rm, yeah, if I write nabla f of the input, I mean this f is something that maps from x to big F of x. If I write this thing, yeah, so then this is by default the Jacobian of f by dx at x transposed. Just notation. This is consistent at least for the case that m is 1, and then it would be a standing vector. That's why I use it. Of course, there exist other conventions, and this is not a very well-defined thing. But yeah, and I can sometimes also write this. By the way, some people write it like this: dx of f, right? So that would be another way, and even another way would be f x of x. But then I will always have the transpose here once I have that one. Okay, and for the second derivative, I will only define it for scalar matrices anyway. So nabla f of x is only for an f that maps from Rn to R. So I will not use this symbol when I have multiple outputs. So that's why this is actually just the Jacobian of this. Okay, so now if I just look at the top, if I differentiate that whole function with respect to lambda, the thing that drops out is actually the f transposed. Yeah, so this is actually f of x and u transposed. The partial derivative of the Hamiltonian with respect to lambda. So if I just note that here I have actually the second derivative of xj times f, because that's what the optimal trajectory will satisfy, and then here I have a d by dt nabla xj, yeah? Then I see that actually this expression and this expression together, they already move to this. Yeah? So I can move this to the left side, combine it with that, and then this is remaining. And so my remaining equation, following from that and from that, will be d lambda star by dt. Yeah, so this thing, and now I move it to the other side, so I have the minus sign here. So this minus sign here, and then from this I will also get a minus sign. Together they just amount to that, but with a minus sign, and I get this dH by dx transpose. Of course, at the optimal trajectory, and maybe I already use my abbreviation with the lambda here. So I get now a beautiful equation. Why is it beautiful? Because it's just an evolution equation that my quantity lambda should satisfy. I mean, this is the optimal lambda, of course. Along the, there is no transpose here, sorry. That it should satisfy along the equation. So basically, it's an equation that my optimal lambda star, the gradient of this value function along my optimal trajectory, should satisfy. And after we have done this hard work, all the rest is basically easy. And we can just collect what we know else about the lambda. Yeah? So what else do we know about this? We know a few things. I mean, we know that at the end we had this condition that the j here at the end time should be equal to the terminal cost. So if we take that series and we can differentiate that, then we directly get the condition that nabla x, j of x and big T should be equal to nabla x of e. I mean, e doesn't depend on anything else than x, so we can directly write it this way. And that means, along an optimal trajectory, we must have that lambda star of big T, because that's what this means, right? At the optimal value, should be equal to the gradient of x at the optimal value at the end. So this gradient relation should hold. So this is one condition. This is another condition that we know our optimal trajectory should satisfy. And these two things, they are determining implicitly our lambdas if we would know the x and the u, right? But of course we don't know the x and the u, and they are all coupled because we know that the u we get from this condition. And so now I would like to collect everything that we know, including the system dynamics, and I will drop the star, because it's just a lot of stars. Yeah? Drop the lambda star, x star, it is, and so on. Yeah? So I will just make lambda x u, okay? Because otherwise everything will have a star anyway. So what do I have? I know that the optimal trajectory x, without a star now, should start at x0. What I also know is that the optimal trajectory x dot should be, maybe I do it this way, it's nice to have zeros, right? Should be equal to f, it's a matter of taste, maybe I don't do it, sorry. So, I know that the optimal trajectory should satisfy the system dynamics, and actually maybe it's better that I drop the star, but I will not drop the t anymore, because I just want to make sure that some things really depend on t. So it's f of x of t and u of t. And this should hold for t on the whole horizon. So that's an ODE that should be satisfied. Then there is this other equation that we just had, so that the u star, the optimal u should be the argument. Did I write it? Argument, yes, that minimizes over all u, the Hamiltonian function of h of t, of lambda of t, and of u. Okay? So if you know the x and the lambda, then you can implicitly find the u. This is all not new, but now the two extra equations that we just had. So now we have this lambda dot equation. That is, I swap the sign, I bring it to that side, and what I get here, and I can also write the gradient here of the Hamiltonian function with respect to x of t, lambda of t, and u of t. So this is already the value that should satisfy that, right? Yeah. And this holds also for t on the time, I mean this all holds for all t, right? It's something that every point on the trajectory needs to satisfy. And then I have a terminal condition that says lambda at the last point, t should be equal to the gradient of e at the last state. That's the last condition. And so these conditions together, they constitute a set of equations. I mean, it's a boundary condition at the beginning, an ODE for x and lambda, an algebraic equation, so to say. I mean, somehow implicitly the u can be found as a function of x and lambda, and a terminal condition on the lambdas, and on the x together, actually. Yeah? So these two things are mixed, as you see. So this is something that looks difficult to solve, right? But once you think of it in terms of ODE boundary value problems, you realize that this is an ODE in 2 times nx states. Yeah? I mean, this one you can eliminate, and in many cases you can eliminate it even explicitly. Then you just plug it into these equations, and then you get explicit expressions for x dot and lambda dot. And so in principle, if you know x 0, which you know, but if you would also know lambda 0, you could even simulate it forward in time. And then the only thing you need to make sure is, so to say, that the lambda at the end satisfies this condition, or that the lambda and the x at the end satisfy this condition. So it has actually, if you look at this, it's a 2-point boundary value problem. Boundary value problem. So it's sometimes abbreviated T, 2-point TP BVP. So very common abbreviation, like PMP, right? And it has 2 times nx ODEs. It has here the states, the control dimension. It's basically, these could be, if you just take the necessary optimality conditions, it would basically be a DIE, yeah? So 2 nx differential states. Which are the x of t and lambda of t. I call it differential states, and it has also NU algebraic states, so to say. So they can be eliminated pointwise via this equation. So if you know x and lambda at one point, then you can in principle also know the u, and in many cases we will actually explicitly write it down. And then how many boundary conditions do we have? We have nx initial conditions. And how many terminal conditions do we have? This dimension of this vector lambda is actually nx again, right? So we have also nx terminal conditions. So if you think of an ODE, if you would know 2 nx initial points, then you could just simulate it forward. Yeah? Because in this case, we don't know all the initial values, we only know the x's. So we cannot really simulate it forward if we don't know lambda 0. But if we would know lambda 0, then we could simulate it forward. And then if we are lucky, this would be satisfied. And if we are not lucky, it will not be satisfied. Yeah? But the fact that we can, so to say, if we would know the nx initial conditions for lambda, that would make an initial value problem, but now we shift, so to say, these nx conditions to the end, and that's what makes it a 2-point boundary value problem and not an initial value problem. Yeah? So it's not an initial value problem, yeah, but let's see, 2-point boundary value problem, but it has exactly the right number of conditions. It has these nx terminal constraints that replace the 2 nx initial conditions that we would have for a well-determined initial value problem. So, so this one you could look at and just say, I would like to solve it, right? And then the question is how you solve it. But maybe I should, before I discuss how to solve it, I should maybe make a few remarks of how to eliminate the u. And no, I think I will already give you, because it's too simple and too nice. Otherwise, the whole beauty is not seen. Yeah? Let me just use the occasion to already explain one of the solution approaches, which is like the most beautiful, but not usually the most stable one. Yeah? So one solution approach it's called indirect single shooting. And if you think of what is shooting all about, shooting is about choosing an initial condition, integrating an ODE, and then checking if it satisfies some conditions. And that's exactly what we will do. Regard lambda 0, it's actually the starting point of this trajectory, as unknown. input to an ODE, or actually it's a DAE if you think of it, namely these equations here. Yeah, so these equations together, I maybe call it equations 2. So if you have lambda 0, and if you have also the x0, then you know, in principle, by forward simulation, you could just use an Euler method or whatever. You wouldn't, maybe Runge-Kutta method, and you would integrate that system of equations forward. In particular, if you have already an explicit expression for the u. Yeah? Assume that you have u of x and lambda, so to say, that would be given. U of x and lambda. So you have somehow eliminated the u. And then you can simulate, basically you can get the state y of t, which I define to be the x of t and the lambda of t together. And then my whole equation is actually y dot is equal to f of x and u, maybe I call this u explicit, right? Explicit of x and lambda. And here I have my dh or my nabla h with respect to x direction, right? So this thing with a minus sign, which also depends on x and on lambda and on u explicit, which also depends on x and lambda, which is the optimizing value. So I have an explicitly written down ODE for these two equations. Yeah? This one is eliminated. These two equations remain. And if I have starting at y0 being x0 and lambda 0. So I start at some points. x0 I know is the right one, lambda 0 is something that I don't know, but if I make a hypothesis, it is this value, then I can in principle solve this ODE. Do you agree? And then, at the end, when I have integrated over the time horizon t, this is satisfied, this is satisfied, this is satisfied, this is satisfied, right? The only thing that I don't know is this. So I check actually if this is satisfied at the end point, and because it has exactly nx conditions, and my unknown itself has also nx unknowns, I have basically a square nonlinear equation system. So I could try to solve that with a Newton's method. So plug the ODE solution into the last equation, which I call maybe 3, into this one. Yeah. And maybe I call this ODE solution y tilde of x0 and lambda 0. Yeah, I call it yt of x0 and lambda 0. So that's the solution, right, for a given initial guess. And then I plug this into the terminal condition, which will actually just be lambda. Yeah? So this is an x tilde and a lambda tilde. Yeah? So this lambda at big T, which depends on x0 and lambda 0, minus this expression here, nabla e, evaluated at x tilde of big T, which depends on x0 and lambda 0. So this equation should be equal to 0. And if you now realize that this is exactly nx conditions for nx unknowns, and the unknowns are lambda 0, then you see that we are actually having a well-posed code finding problem. Yeah? And that's also one of the numerical methods which people use to solve optimal control problems with the indirect approach. I mean, the most elegant if you think so, because I mean, it's extremely strange if you think of it. So once you have found the right lambda 0, yeah, given this equation system here, you can just find the whole optimal trajectory just as a function of this one dimension, I mean not one, but the nx dimensional vector. Yeah, so you have one vector of the dimension of the state. And if you know this magic initial value for lambda, you can just simulate your primal dual or the nominal and the adjoint system together forward in time, and you get the whole trajectory, all the optimal controls, all the x's, all the lambdas, everything, just as a function of this magic first multiplier. So it's a quite condensed form of summarizing the solution of an optimal control problem, and that's what makes people very excited. And I should also say that it has a very nice computational advantage, because when you formulate these ODEs, you can actually just solve them with the time-stepping method. You can actually, you don't need to remember all the trajectories in principle, and you could also propagate derivatives of that with you, with the forward approach of AD. But in times where we didn't have much memory for computers, this was really advantageous, because you could basically just, have a lambda, and then you propagate it to the end, then you check the terminal condition. You also have the derivatives of this condition with respect to lambda 0, and then you can do a Newton's method. So you can solve it with Newton's method. So that's the rough idea in 1 hour. What is this indirect approach about, and why are people excited about it? Yeah? Of course, there are many details, and I should also say that some of the details we will discuss. One is how do we get this u really as an explicit function of the x and the lambda. The second one is, and that's a bit unfortunate actually, is that the forward simulation of that ODE is not without problems usually. I mean, it turns out that if this f is a very stable system, then this is a very unstable system. So it means that this f, if it's contracting, this lambda dynamics, if you integrate it forward in time, will be expanding. And that means that you very quickly go into maybe even explosions, undefined areas of this ODE. So it's not a very easy ODE to simulate forward in time. And for that reason, you do not solve all problems with this beautiful method. But some you can solve, and until today, actually, people solve, for example, the planning problems for some satellite orbits, which need to do maybe 300 revolutions around a planet before they go, and some higher orbits, they can be solved with this method. Many other problems cannot be solved with it, but some can. And there it's really beautiful. So that's why I wanted to present it, and next, after the break, we will discuss a few details of this approach. Yeah? I hope you got the idea already, and we meet at 15 past again. Okay, so let us continue. And as promised, I wanted to say a few words and give a few examples on how to make this work, so to say, in practice. And I want to start with the question of how to obtain the controls as an explicit function of x and lambda. Yeah, because that's one ingredient that we need. So we are now in section 12.2. Obtaining controls as a function of lambda and x. So the aim is that we get an explicit function u star of t should be given as some function u explicit that depends only on x of t and lambda of t. Now I put the star again. So I need to get the function u explicit of x and lambda, and that is the aim. And of course I know where I get it from. It's the argument that minimizes the Hamiltonian over all u for a given x and lambda. So that's what actually is the definition. But how does it work in practice? Let's just look at it. Yeah? So the easy case is called regular. And because this all is about arcs, so I mean the optimal control solution turns out to be divided into different arcs typically. Sometimes we call it a regular arc. So on a regular arc, something like the following will happen. And there we have actually the condition that the dh by dx, by du at x and lambda at the optimal solution. But this derivative is invertible. That means that you can get the u as an explicit equation. I mean, this equation system, maybe I should keep it this way, that should be, there should be a u that explicitly appears, and then I can actually just bring the u to one side, and then I have an explicit expression. Yeah? And it turns out that this is invertible if the second derivative is positive, right? And actually what you need is that the Hessian matrix of this thing with respect to the u's at x star and lambda star and u star is positive definite. Because if it would be negative definite, then you would get some unbounded solution. So that's for minimizing, we need positive definiteness. But this is basically an invertible matrix, and if it's invertible, then we can be happy, because then this will be a nice invertible expression. So let me just give you one example where this is definitely the case, and that's actually the example of linear quadratic regulator. So let me just choose L of x and u being 1/2 x transpose qx plus 1/2 u transpose ru, and what I will choose is r positive definite. Okay, and then of course my system dynamics I will also assume to be linear, ax plus bu, and then what is my Hamiltonian? X of lambda and u. What will it be? It will be L plus lambda transpose times f, but that is actually 1/2 x transpose qx plus 1/2 u transpose ru plus lambda transpose ax plus bu. So now I need to see if my derivative, this optimality condition that I have for minimization with respect to u, So what is this? Let me just compute it first as a general derivative. So if I differentiate that with respect to u, nothing appears here, something appears here, and here actually, okay, maybe I should, no, it's okay. I'll just leave it like that. That's actually a lying vector, a gradient, so I have to write it this way, right? That would be this derivative, plus then here I have that derivative that is lambda transpose b, okay? And now I need to set this to 0. And this will be equivalent, of course, to just saying that the, well, okay, maybe first I transpose it, and it's more usual. Yeah? So ru is equal to minus b transpose lambda, right? And that is equivalent again to just saying u explicit of x and lambda is given as minus r to the minus 1 times b transpose times lambda. So interestingly, in this case, it doesn't even depend on x, but that's just an accident. Some other examples, it wouldn't be the case. But you see now I have an explicit function of how the u depends on x and lambda. And I can eliminate it now. So what would be the 2-point boundary value problem in this approach? Let me write it down. The TP BVP would be x0 being x0. Then I have my differential equation, x dot equals, and now it should be, maybe I write it down, it's f of x and u, right? But at the optimum, so in this case it will be a x plus b u star, but u star is given by this expression, minus r to the minus 1 b transpose lambda. So it will be actually given by, this was just intermediate, I write down x dot equals a minus b r to the minus 1 b transpose times lambda. Sorry, and this is ax. So this is now my equation for x. Now I get also an equation for lambda. Lambda dot is equal to minus the gradient of the Hamiltonian with respect to x. So let me just look at this Hamiltonian here. So again, a little computation in the back. So what is the maybe dH by dx? If you look at the expression of the Hamiltonian, so the first thing is that it will be x transpose q. That's the first part. The second term doesn't depend on x, but then the last one is lambda transpose A, right? Plus lambda transpose A. And if I transpose it to get the gradient, then I get here minus q x minus A transpose lambda. So this was just intermediate, everything here. And now I write on it in clean. Lambda dot is equal to minus qx minus A transpose lambda. Very simple, just an expression on x and lambda. These two equations should hold for all t, of course, it's the trajectories, but then I have the terminal condition, and maybe I should also make the assumption, of course, that E of x, the terminal cost, is given by 1/2 x transpose px, like before, for linear quadratic forms, right? So then I know that the gradient of E is given by px. And now I have this terminal condition that says that lambda at the endpoint should be equal to the gradient p times x at the endpoint, right? So that is my terminal condition now. And if I collect it all, and this is what I want to do, I could call now y, the x and the lambda together. And I can create a new matrix that maybe I call A bar. A bar is now the dynamics of the y. And what dynamics will it be? So I know now that y dot, which is of course x dot and lambda dot, is given by, now I collect all these equations, it's A, I make here x and a lambda. So it's A from this x here. And then it's minus b r to the minus 1 b transpose. So minus b r to the minus 1 b transpose here. Then here I get a minus q. And here I get a minus a transpose. Okay, so this matrix I will just call A bar. So you see basically that my dynamics is now y dot equals A bar times y. And if I put my exponential solution, I mean, I really want to solve this problem now, right? So what should I do now in the single shooting approach? I would just say y of 0 is given by x0 and lambda 0. I have now, what do I need to do? I need to solve now the initial value problem, so I can get actually y of t is, it's just an autonomous system without input, right? So it's actually exponential of this matrix A bar times the initial condition, y0. And now I can evaluate that, sorry, this was times t here, right? And I can evaluate it in particular at the end point. So my really interesting point is actually this thing that I get at the end. So x of big T and lambda of big T. This vector I get as the matrix exponential of A bar times big T. This is a big matrix, right? 2 times the state dimension. Times the initial conditions that I have here at x0 and lambda 0. So because the x0 is fixed, the lambda 0 is just an unknown, I can generate from the lambda 0 the linear map that gives me x and lambda at the end. Now I plug this into that equation here, right? And what will it be? It will be, maybe I write it this way, okay? Or maybe with the other sign, that's a bit more convenient. Then I see that if I just multiply P times minus a unit matrix times x big T and lambda big T, this should be equal to 0, right? So that's what this equation is. I see that this thing even can be eliminated, and so my only equation system that I need to solve at the end is actually this one. I have P and minus unit matrix. Then this exponential A big T. And here I have my x0 and my lambda 0. So that should be equal to 0, right? And if you think of it, this is a matrix, I mean, this is nx conditions, nx by nx, if you regard only lambda 0 as an unknown. Yeah? So this x0 is, of course, fixed. So you see that I have basically a square system, square linear system. I can just solve it. And I have solved my optimal control problem. Would be really nice. Please note that we didn't even solve a Riccati equation or anything here, right? So we just had this matrix exponential, which is of course also a very expensive thing, but anyway, so it can be at least written down in a very simple way. So this way we can solve LQR problems relatively quickly. Other questions? This was maybe fast. Do you see that this is a square system, or should I make that a bit more explicit? Actually, there would be one way to make it even more explicit as a linear system. I could just say, actually, this expression here I could decompose. Maybe I do it on this blackboard into one constant term, which is actually this thing, a bar big T times x0 and then a 0 here. It's a constant vector, just a standing vector. And then plus this b minus 1, this same exponential a bar big T times, now I add here matrix, which is a unit matrix of suitable dimensions times lambda 0, right? So it's actually exactly what we have here. And this whole thing I set to 0. And then you see that this matrix needs to be inverted. So this I call maybe M. Yeah. This whole thing I could call V. Vector and matrix. Yeah. And then I just get this equation system M lambda 0 equals minus V. And I need to solve it. So I see lambda 0 equal to minus M to the minus 1 times V. So this way I have solved my initial lambda 0, and then with this lambda 0 I could get in principle the whole trajectories by this forward exponential expression. Yeah, so this would be like the most beautiful case for solution of an optimization problem with the indirect approach. But the main message is that I would like to convey is that you basically reduce everything to finding the initial multiplier, and that's like the real power and the real beauty of it. But as I said, this is like the nicest case only, and there are many other cases which are not so nice, unfortunately. And this is appearing in some applications, and often we have this fact that this session here is not positive definite. And that's a really unfortunate fact then. If it's not the case, this whole inversion that we did here is not possible. And I can give you an example, but maybe I just explain a bit why this could happen. I mean, if you look at the Hamiltonian function that we have here in this example, you see that it directly depends on u. And it depends on u in a quadratic fashion because of this R matrix. If you take the second derivative of it, of course, this will have a second derivative of u. So if there wouldn't be this term with the R, and you would two derivatives, there would be no second derivative of u, and it would just be 0. This thing would be just 0. And then there is no chance to actually retrieve your your u. But this can happen in applications, and it's not uncommon, unfortunately. And people have developed methods to deal with that case, and they all go the following. They say, actually, this optimality condition, this fact that the dH by du should be equal to 0, this should hold along a trajectory anyway, even though this might not be an equation that actually helps you to find the u, it should still hold, right, along the optimal trajectory, because it's this optimality condition. So what you can do is you can differentiate that further. Now I just say this whole thing I differentiate again with respect to time, and again and again and again, and because it's all 0, I need to, along the trajectory, all the derivatives should also be 0. And that's the trick, and at some point, if you're lucky, and actually it turns out that you will be lucky at some point, the u will pop up and you can invert it. Yeah? So the idea is to differentiate further if, with respect to time. And because along an optimal trajectory, this quantity should always be 0. So what you will do is, so to say, you will say dh, I mean here the nth time derivative of x along the optimal trajectory. Maybe for safety I add the star here everywhere. So this is what you want to, and here's one derivative with respect to u. Yeah, so this should all be 0, and I just do it again and again, and at some point I hope that the u appears. Yeah, n large enough to make u appear explicitly. And this sounds a bit silly, but it's not silly, sorry. The point is, if I differentiate that whole thing with respect to t again, then please note that because this depends on t, there will be an x dot appearing, but the x dot I can then replace by the f. And there will be also a lambda dot appearing, which I can then replace by the gradient of the Hamiltonian, because I know them. And that's the way to go on, and at some point you are lucky. So I will give you an example. And this example is just x u is the same as before, but I have just discussed 1/2 x transpose q x. That's it. Nothing more. And the system dynamics is still as before, f of x and u being ax plus bu. And now my Hamiltonian as before, x lambda u is 1/2 x transpose qx plus lambda transpose ax plus bu. Okay? And my equations are similar, but what is dh by du? It is now just lambda transpose bu. That's it. This is bad, right? So now I differentiate that thing with respect to, so not even, this u is not there. So this I need to differentiate again. Maybe I keep in mind what, no, maybe I first do it. So let me just write dh, du, and this whole thing totally differentiated with respect to time. So I need to, what I will get is actually lambda dot transpose b. So now lambda dot I know is minus the gradient of x of the Hamiltonian, which I get, I see it, it's actually okay, minus qx here, and here I get minus a transpose lambda, right? So that is what I had before. So now I can get this in, and of course I need to transpose it. So I put the minus sign in front, and then I have here, and here I have now a lambda transpose a plus x transpose q. So now I plugged basically the lambda dot expression into this place. Does the u appear? No, unfortunately not. So I go on. d2 dt squared of dh du. So I just go on. So what I will get is lambda dot transpose A plus X dot transpose Q times B. I mean, all the other data are fortunately matrices in this case, so it's relatively easy. So now I plug in the same expressions that I had before. Let me just do it. So first I get this. This was lambda dot, right? So I replace that with what I had before. The minus sign cancelled for that, so I get actually lambda transpose A plus X transpose Q for this. Then I transpose it. Oh, this was already transposed, right? Then I get the A here. That's for this term. And then I get this term where I still have the minus sign. AX dot is actually just AX plus BU transposed, right? Times Q. Okay, and then the whole thing still multiplied with B. Does the U appear? Yeah, somewhere. So I have some hope. Let's see. So let me just reorder these things a bit and maybe also remove the transposition. I transpose it, so the whole thing I transpose to make it a bit nicer. And I know actually that this whole thing should be 0. So I say 0 should be equal to, and now I order all these things. I get B transpose. Maybe I bring this first to the other side. So then I have a Q. Q was symmetric. Yeah, I think I will not bring it to the other side. Let me first start with this, otherwise it's too confusing. So I take that one. So what is it? It's A transpose, and then here I get an A transpose, I have lambda, that's from this term, then I get plus A transpose times Q times X, right? So that's from this term. And I think I forgot the B, right? So 0, here is a B transpose, and here should also be a B transpose from that one. And then I get the minus, and then I have a B transpose times Q, and I separate it into this term first. That will be something very strange at the moment. No, it's on the other side, right? Okay, it's just AX. Okay, and then I get this last term, which is this one, and then I get B transpose Q B times U. I think this should be correct now. So this whole thing should be 0, and there is one appearance of U. Here is a lambda, here is an X, here is an X. This thing looks even a bit similar, but not exactly. I mean, there's like this matrix seems to be anti-symmetrized, but don't worry. So the whole thing is, if this matrix is invertible, which I would hope, which is not necessarily the case, but maybe I'm lucky. Yeah? If that is invertible, I assume it, then I can just say U star is equal, I should put this matrix B transpose Q B to the minus 1, and then all this, what I have on the other side is actually lambda X, X, okay? So now, under this, if I'm lucky enough, and this is an invertible matrix, I will be okay. If it's not, I would differentiate further. And after 2 more differentiations, I will get another term with some new U's appearing, and so on. It can be very tedious, as you see. And that's also one of the reasons why the indirect approach is not so much used by, let's say, the non-mathematical optimizers. Wow. I really close the window. Or a few at least on this side, because it's so maybe I should tell you one more thing, which is also very surprising and which makes working with the indirect approach sometimes very, very fun. So if you have path constraints, yeah, this is a section that I will also summarize only very briefly, but it's 12.3. Pontryagin with path constraints. And maybe when I say path constraints, then I will also, in this case, only regard the the regular case. There exist nastier ones, and they very often appear. But the regular case is that you can get actually the U star. Maybe I should say that I have now in my optimization problem also these constraints. But on the whole time horizon, I would like to have these constraints. And I will not derive the Pontryagin maximum principle for this, but that was actually the main point of Pontryagins work, that he generalized this whole calculus that we derived so far also for the case with control constraints and with state constraints even. But the surprising outcome at the end is actually that U star of t can be obtained as arc min of all the U's that minimize this Hamiltonian function of x, lambda, and U, but subject to the path constraints. So in the case that this depends explicitly on U, this is easy. Yeah? And that's what I will assume, because then for fixed x and for fixed lambda, this is a nice optimization problem in U. Imagine what would happen if there is no U appearing here, then this is completely unsolvable by minimizing U, right? So then there is no degree of freedom, and then you get a singular situation like a bit like that what we had before. Yeah? So assume h of x and U depends on U. So then you can have this nice expression here. And the interesting thing is that you can actually just get this, you can solve this explicitly in some cases, and in the most beautiful cases you can do it. And one example where you can actually solve it explicitly would be the case where you have an L of x and U, which is given by, let me just, I think I can make it as general as possible. Let me just make it as general as possible. I have an 1/2 x transpose qx plus 1/2 u transpose r u. And my r is diagonal with some entries up to, I mean, all these numbers are positive definite. So it's a very simple thing. You know? And my f of x and u would be given by ax plus bu. And now the interesting thing is what I want to add. I want to add path constraints. So I have a minimum and a maximum for all components. So now if I have this minimum and this maximum, I could ask, how do I solve this optimization problem? So what do I need to solve? I need to solve minimizing h of x lambda u over all u, subject to u min smaller than u max. Actually, I could, yeah, don't worry. I just leave it this way. So now this could be an optimization problem I could try to solve. And interestingly, if I solve the unconstrained one with this one, I know the solution. It's the one that we got here, right? Where was it? Here. Where was it? There. This one, right? So it was r to the -1 times b transpose times lambda. But u star or u explicit can be, in this case, as a function of x and lambda, can be shown to be something that is similar to what we had here, r to the -1 times b transpose times lambda. But due to the fact that we have these constraints, and due to the fact that our Hessian is diagonal, it turns out that our solution can be obtained by clipping this actually to the domain where we are inside this min and this max. So I could actually compute the I don't want. I want that this whole thing is not bigger than u max, so I will somehow take at some point the minimum of this with u max. So these are two vectors, and I take for each component the minimum of the two. And then I get a new vector, which is never bigger than u max, right? Because either it's this smaller or that is smaller. And then I take the max of that vector with u min. And by that I get rid of everything. If this whole expression here would be lower than u min, then because I maximize over this and u min, I will get this one. So if it would be one component, then here is lambda and here is ux. Then it would look something like this, like a saturation function. But if it's multiple components, it will be a bit more complicated. But this expression is still an explicit expression on my controls, and I could plug it into my equations here. And of course, this gets a horribly nonlinear dynamics, so it's actually even non-smooth, right? So that not as it's not second differentiable, but it's at least it's a Lipschitz function, right? I mean, it's just nice from that perspective. So it will be still a well-defined simulation problem, and you can, in principle, still solve it with an ODE solver and hope to get something meaningful. Of course, the order of the ODE solver will not really be played or used. Yeah, there's a question.
Would it help if we replace the saturation function with one that's differentiable, like, for example, the logistics function?
Exactly. So you could also, and that is sometimes done, you could make this a bit smooth, so to say, right? Make a soft max and a soft min and so on. Actually, soft max has a different meaning in computer science, so maybe I shouldn't use that word, but basically that's what you can do in practice, and that would correspond roughly to augmenting the cost function with a barrier penalty. I mean, you could just think of this L of x and u being something that has the usual quadratic term that we just had, plus a barrier that penalizes everything that's out of bounds. Yeah? So here would be u min and here's u max. And if you make a smooth barrier, then you basically will get as the explicit solution, but it would be very tedious to write it down because these would be logarithmic barrier terms. You would have to set them to 0 and then solve this equation in order to get the u. But roughly speaking, it would correspond to something smooth, where you would just have the theory from before applied to a smooth barrier function. And then, yeah, even our derivation would still hold. Yeah? But it would be not so nice or not so easy to write it down in practice. So I just wanted to say, if you encounter a problem with just one single variable, for example, and bounds, you can very explicitly solve it, and you can still apply the whole algorithm of this forward shooting method and hope to get solutions. And that's what is done sometimes. Yes?
Well, that might not be an optimal solution, would it? I mean, we had an exercise where we had such a problem.
Yeah, that is the current exercise, yeah.
Or we had a previous exercise too, where that needed to be applied.
Yeah.
And so that would not be an optimal solution. Is there any way to make that, get an optimal solution?
What do you mean by an optimal solution?
For the boundary problem.
I mean, when you make it smooth, or what is your question?
Yeah. For the non-smooth case.
Sorry?
The non-smooth case would be fine as well.
So maybe I tell you what you can do in practice. You just take the non-smooth expression that I wrote down there, not even making the corner smooth. You apply even a high order integration method, even though it's strictly speaking not really applicable. You go through the whole integrator, differentiate it, you do your Newton's method, and then you get a solution. That's a high accuracy solution at the end, surprisingly, if you can solve the boundary value problem. Okay, so actually this lecture, I should say, and you see it from the time I devote to this thing, is not about Pontryagin, and it's also not about the Hamilton-Jacobi-Bellman equation. So there are full lectures on that, because yeah, this lecture is about numerical optimal control for science and engineering. So most people in science and engineering, I mean not in mathematics, but in particular in engineering and applications, they use the so-called direct methods, which is what we have basically treated in the discrete time case already, but which we will now connect to to the continuous time formulations a bit more in detail. So this was just a very short tour de force through approaches that are used, but maybe not so easily used in basically default applications. And that's why in the next lectures we want to go to, how do we call the next chapter? To the so-called direct approaches, which directly address the optimization problem. And we do directly address it by not looking at the continuous time optimality conditions like we do here, but we do it by this relatively straightforward and direct approach of discretizing first the controls and then having a nonlinear program and then solving that one. That's what we did in the first two parts of the lecture, right? So we will discuss a bit how we come from infinite dimensional optimal control to a finite dimensional problem in the next chapters so that we can forget about all this again. Yeah? But there are a few things we should keep in mind, and the few things I would like you to keep in mind is first that the lambdas have really a meaning. You remember in dynamic programming already, the lambdas for the continuity conditions are the gradient of the value function. That's also true in continuous time. Yeah, maybe the other thing is that at the end, we don't have it here anymore, this boundary value problem that we have in the indirect approach, basically they are necessary optimality conditions. They are very much related to the KKT conditions, but in continuous time. So please keep in mind that when we formulate also in direct approaches necessary optimality conditions, from some perspectives they will be similar to a discretization of the Pontryagin equations. So that's a relation that sometimes pops up, so to say. But apart from that, after doing maybe one exercise with Pontryagin, practice and see how beautiful it is, but also seeing maybe how difficult it is to find the lambda zero, and also to derive the explicit expressions for the controls. After you get a taste of it, we will forget about it again, and we go on with the direct approaches. Anyway, the lecture is nearly over, but we will see that everything we learned until now was basically for the direct approaches. That's why I didn't say it, but basically everything you have learned in the first two parts of the lecture is about direct approaches, so we can build on it. So for today, we finish the Pontryagin chapter, and we go next week, I should say next Wednesday. We go on with the direct approaches. So maybe I should say that next Wednesday, not this Wednesday. This Wednesday there will be no lecture. It's completely cancelled, and also the Monday afterwards is completely cancelled because I will be on outside events, unfortunately. So the next lecture will be only on Wednesday in a week. Okay? So I wish you a wonderful week. See you.